Carving tracing of strain characteristics in Cartesian coordinates for composite beams. This is the topic mathematics subject. My name is B. Saicharan. I am from Data Science Department. Introduction to Composite Beam Mechanics. The stress strain behavior is non-homogeneous due to material property differences across the cross section. Composite action relies on strain compatibility at the interface between constant materials. Stress distribution is derived using transformed section method to account for material heterogeneity. Curve tracing reveals the nonlinear elastic in elastic response under bending and stress strain fundamentals in Cartesian coordinates. Stress means sigma bond and strain means summation or scalar function. These two are stress and strain are scalar functions of positions x comma y of cross section in the beam. The conjugate relation is sigma of x comma y equal to E of x comma y summation x comma y varies with material zones. Principal axes are aligned with the Cartesian coordinate system to decouple bending and axial effects. Strain varies linearly with depth. Summation of y equal to summation c plus ky. The summation c is centroidal strain and k is curvature. In summation c is centroidal strain and k is curvature. Transformed section method. The transformed section method homogenizes composite cross sections by scaling material areas by E ratio equal to EI by E ref. This converts the composite section into an equivalent homogeneous section for analysis. Neutral axis location is recollected in the transformed section to satisfy force equilibrium. Moments of inertia Lx, Ly are computed on the transform section for bending analysis. Stress recovery is achieved by scaling transform stresses back to original material moduli. 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 The neutral axis. Na is the locus of the zero strain in the cross section under bending. Strain compatibility ensures summation top by summation bottom equal to y top by y bottom preserving plane sections assumption. For composite beams, Na position depends on E ratio and material distribution across depth. Na shifts occurs during nonlinear response due to material yielding or cracking. Iterative methods, example bisection, are used to locate Na. Na means composite beams. Consecutive models are nonlinear. Linearistic stress strain tracing. In linearistic region, sigma of y equal to E of y summation y equal to E of y summation c plus ky. Stress profile is piecewise linear with a discontinuous material interface. Bending moment m of integral of sigma of y dya equal to sigma of ey summation c plus ky dA over the cross section. Is axial force n equal to integral of sigma y dA equal to integral of E of y summation c plus ky dA. Nonlinear consecutive models for materials. This is Ramberg-Osgood model. Linearistic for linear, elastic up to brittle failure at summation unity. Ramberg-Osgood model sigma equal to summation equal to sigma by E plus alpha of sigma by sigma of 0 to the power of n for metals. Numerical integration for stress resistance. Stress resultants are computed by a numerical integration Gaussian coordinate across materials. Nonlinear sigma of summation m equal to integral of sigma of summation y of y dA requires solving f of summation c comma k equal to 0 for equilibrium. Newton-Raphson method solves the nonlinear for summation c and given m and n. Strain increments are applied to stress full strain envelopes. Convergence criteria include residual force tolerance and stress increment size control. Moment curvature Km relationship. The Km curvature traces beam response from elastic to collapse. Elastic limit. This elastic limit yielding occurs in maximum material reaches summation of y. Elastic limit is d. This then axial strain force summation c comma c minus in relationship. The summation cn curve describes action response under tension and comprehension. Interaction diagrams. P delta and geometric nonlinearity effects. Second order effects. P of pi. Simplify, amplify moments in slender composite beams, total strain. Summation y equal to summation c plus k of y plus into lateral deflection. Curve tracing must include object geometry via incremental iterative methods. Buckling load is defined when the width increasing. Curvature of Km curve differential geometry. This is an differential geometry of stress strain curves. Curvature of Km curve. Km curve of curvature in differential geometry, stress strain curves, curvature of Km curve, dk by dm equal to 1 to 1 by dm by dk, where dm by dk is stiffness. In this case, dm by dk is stiffness. Inflection points indicate material yielding or cracking. Area under Km curve represents energy absorption capacity. Tangent stiffness matrix Kt equal to dr by du is used FEM implementation. Curve fitting. Finite element modeling of composite beam FEM. FEM discretes beam into 1D elements with composite cross sections. FEM means finite element modeling. Each element has multiple material layers with independent sigma summation laws. Gauss point integrate stresses across cross section at each node. Okay, at each node, global stiffness matrix K equal to integral of b to the power of t d into b dv comma where d is material matrix. In this case, d is a material matrix. Post processing stress km summation c n curves from nodal forces and displacements. Limit states at failure criteria: material failed, strain compatibility failed, buckling global, ductile versus ductile versus brittle failure. Limit states. These and 4-point bending tests measure Km response using strain gases, LVDTs, digital images, low displacement curves convert into Km via K equal to this one. Applications. This is failure trends. In this case, we can conclude we can conclude in composite beams of Cartesian coordinates. In this case, we have learned easily Cartesian coordinates of composite beams. Okay, thank you.